This lecture is going to be on the chemistry of the river water within the Middle Fork River. We're going to be able to talk through the quantifiable testing that we'll be doing looking at the river water itself, and this is kind of sponsored by our friends at the Chicago River. But first, let's meet our student. Look at this class. What a great class. So the parameters we're going to be testing are going to involve turbidity, really kind of the how murky or not murky the water is, so how clear, kind of a measurement of clarity. Temperature, and this is going to be kind of an easy one. It's just going to measure the difference of temperature at two different locations, and really the temperature permits what can and cannot live in the water itself. pH is an important feature because it's going to determine the rate at which metabolic processes can take place. So the pH is going to determine if and what organisms can live in the water itself. Moving on here, dissolved oxygen, a very important feature, very important factor in determining water quality. So the more dissolved oxygen, typically the healthier the water is, and the less the value in parts per million. Here you'll see these values. You really begin stressing organisms, and the lower you get of dissolved oxygen, the highest weighing factor, which we'll get into here very shortly. We've got nitrates and phosphates. These are values, well, these will be a couple of substances that come in fertilizers, and phosphates also are found in soaps and detergents that are kind of scoured off the local land, and they find their way into the Middle Fork River, or any river or stream for that matter. And this is a summary as to the 9 parameters, but we're not doing all 9 parameters in this class. It's not the scope and scale of what we'll be able to do, but we will be testing for pH. That's easy with litmus paper. Phosphate, nitrate, and DO. We'll be using the Hawk spectrophotometer for these 3. We will also be looking at turbidity. We will be using a Secchi disc, and then change in temperature, we'll just be using a digital thermometer. Now notice, these are the expected ranges, and these ranges are all based on what the test is on. So this is going to be a wide, highly variable here. Units, this milligrams per liter, this is equivalent to parts per million. Obviously temperature, degrees Celsius. Turbidity is in centimeters, and we're not going to be measuring fecal coliform, but these are in colonies per 100 milliliters. So, and then in the end, we'll be talking about water quality, and that's really where we want to take this. So this is the analytical aspect, and this is where the Q value is simply identifying a way of, well, let's just say standardizing all the different water quality test results. So we're going to be getting these numbers, and the numbers don't mean much until we begin to plug them into these graphs to begin standardizing that. And this is where we're going to be using our y-axis measurements, right? This is why we use the values we take. The values we get are typically found on the x-axis, and then we get this Q value, which is a standard measure of, that's going to allow us to put all of these combinations together, or at least the 6 we're working with, to make sense of talking about a comprehensive explanation of the river water quality. So here I have pH, here I have dissolved oxygen. We will wait to do dissolved oxygen because there's a step we'll have to do before this. So I'll instruct you how to do that when we get back. Here's, we got phosphate, here we have nitrate, and we'll also be working with temperature difference, right? Delta T, if you can see this on this x-axis here. And last but not least, turbidity. There's a step before turbidity. You'll have to convert that into an NTU value, right? So the greater the depth you can see into the water, the greater the NTU value. And typically that is going to influence the turbidity of the water. So notice, just like grades on a test, what we come up with our values, this overall water quality, a clever way that some hydrologists call it is WALITY. You won't hear me use that very often, if at all. Notice that it's just like an exam score, 90 to 80%, 90 to 100%, excuse me, excellent water quality, 70 to 89%. Notice this isn't exactly 89 to 80%. Notice the 70 is good, and then 69 to 50%, or 50 to 69% medium, 25 to 49% is bad, and 0 to 24% is very bad. So more often than not, you'd be surprised that the Middle Fork River water quality is somewhere between the good and medium. I've yet to ever quantify it in the bad column. So we'll make sure that our data does the talking for us, that we're not jumping to too many foregone conclusions prior to testing. So I'm going to walk you through an example set of data, and we'll be able to solve and go through this together. So check this out. Let's start off with turbidity, and understand that the expected range is between 2 and 140 centimeters. We measure this with what's called a Secchi disc, And our test value, let's say that we get a value of 60 centimeters, which is kind of some comprehensive value. This is actual data from a past class, so we're going to go ahead and roll with this. Notice 60 centimeters. So we're going to go back and use the chart that is on this page here. And I want to look at this for a second. Because we are working with turbidity, we're going to be working in this corner down here. So give me a second to make it enlarge. So let's look at just turbidity. We said that it was 60 centimeters. So it's important that we use our turbidity conversion chart and find 60 centimeters in here. So you'll notice that these are the values in centimeters, and we're going to correspond that to an NTU value. And 60 centimeters here is, here I have a value of 57 to 60, and we're going to go with the value of 8. So if I look at this value of 8 here, I'm going to find my NTU value of 8. And I'm going to go ahead and find it. Notice it's in my this first little square that's a value of 10 within here. So I'm going to kind of use this scale, not kind of, but I'm going to go ahead and follow this 8 up here. I used 8, and it's nice because it intersects with the 80%, or this 80 Q value. And this Q value score is simply that grade for turbidity. So 80 isn't a bad overall score, but this is how we use our Q value charts to help make sense of this. So now if I go back to this page right here, to the data collection, I know that this scored a Q value of 80. And now in order to find my overall total here, I'm going to take my Q value of 80 and multiply it times 0.08. And I'm going to get a value of 6.4. Now I'm going to come back and use this number a little bit later. So we'll come back to that. So secondly, I'm going to try to walk you through, let me highlight and make that one red. Highlight, these are temperature differences of 12.2 degrees C and 11.2 degrees C. And I'm going to show you how to do the Q value for the change in temperature. So notice the difference is 1.1 degrees C. So we're going to take that value and go back to our Q value chart. So if I use the 1.1 degree difference, you'll notice that 0 change is going to have the most optimal value in the low 90s. But 1.1 is going to be kind of somewhere in between here. Notice my scaling factor in this little square here, in each of these, are 5 units. So in this case, 1.5, it was a positive value. I come over here, 1.5, we'll just say it's roughly 90%. So we're going to use 90%, or 90 as our Q value. Okay, so let's go ahead and put our Q value in of 90. Wow, it looks like a good score. 90 times 0.1, or 0.1 here, I get a value here of 9.0. So in the end, we're going to come back and use all these values, and we're going to quantify the overall health. Next, let's do pH. I get a value of 7.6. So we take our pH value of 7.6, I find that on my x-axis. Remember, I'm looking for my Q value score over here, so I find 7.6 roughly in the middle. I come up here, and I get a value of roughly, let's call this 92, right? If I travel over here and follow this value, I get a 92. So let's go back to our data chart. So I bring that 92 over here, and I'll go ahead and plug that in. I get a 92 Q value. I'm going to multiply it times the weighing factor of 0.11. And I get a value here of 10.12. Next, we'll do phosphate. Phosphate, we do the same thing as we did prior. So for phosphate, it had a value of 2 on my x-axis here, the milligrams per liter, which is another value of parts per million. They are synonymous. You'll notice that this is a really low Q value score. Q value score here, we'll call that roughly, we'll go with 26. If I extrapolate that over here, draw a line. So we'll call that roughly 20. So here I have a value of 26, pretty low, times 0.1, that gives me a value of 2.6. And this is kind of the beginning phases of learning how to do this. I'm already up to 9 minutes of videoing, so I'm going to stop it right here. Nitrate, same way as all these other tests. Dissolved oxygen is a little harder, there's an extra step in there. We'll do that in class next week. All right, best of luck. See you soon, bye.